So to implement a dictionary using a binary search tree, we previously said that a lot of the operations take the runtime is proportional to the height of the tree. So if we have a height of a tree that's as maximal as possible, something like this, where everything is chained, and we want to search for something, we have to go all the way down, and that might be, O of n sort of runtime, then that's not very fast. Rather, if it was something like this, which was nice and balanced, then that's a lot quicker, right? So we go here, it's not O of n, but rather it's O of log n, right? So we make a huge improvement from O of n to O of log n, right? So this is logarithmic time because we're just searching log n levels deep. So how can we sort of guarantee that we can search in logarithmic time, and insertion taking logarithmic time, deletion taking logarithmic time, as compared to what we had previously with just a general textbook binary search tree? Well, we'll talk about this process called augmenting a data structure in just a bit, but for now I want to introduce AVL trees. So AVL trees are an example. AVL trees are an example of an augmented data structure, and AVL trees are in fact augmented binary search trees. So they are binary search trees, but they have some special operations and special properties which are implemented very well. So in industry, there are other augmentations of the binary search tree, such as red-black trees and things like that, and a lot of the other ones are often used in industry, maybe a little more than AVL, but the one we'll talk about for our purposes is this AVL tree. So okay, so what is this AVL tree? Again, it's a binary search tree which is AVL balanced. It's AVL balanced. And if you don't know what this means, don't worry about it too much. You'll see in just a second. But AVL balanced is sort of referring to the fact that all the nodes in this tree, so in this tree, are AVL nodes. And what this means, if a node is an AVL node, then this means that their balance factor, is either -1, 0, or 1. Right? So their balance factor is -1, 0, or 1. Well, we haven't really defined what balance factor means yet. So let's define what balance factor is, right? Okay, so balance factor. So balance factor refers to the height of the right subtree minus the height of the left subtree. And if we have the case that this height of the left subtree minus or rather height of the right subtree minus height of the left subtree is or rather the absolute value of this is lesser or equal than 1, then we have that this is an AVL node, or this is what suggests we have this property called the AVL invariant. AVL invariant. Invariant sort of satisfied. So this AVL invariant, if it's satisfied for all the nodes, then indeed we have an AVL tree. And one thing I just want to talk about is just some lingo, and we say that if the balance factor for some node is -1, that means it is left heavy. It is left heavy. And if it's 0, then it's balanced. And if it's 1, then as you can guess, it's right heavy. Okay, so it can be left heavy if it's -1, right heavy if it's 1, or it could be balanced if the balance factor is 0. Okay, so let's get that out of the way. Alright, so the height of an AVL tree with n nodes, the height of an AVL tree with n nodes is equal to, well, we can't say for sure what it is because it can slightly vary, but we can sort of bound it. We say that it's in theta of log n, right? It's in theta of log n because remember what an AVL tree is. It's special because it is very much balanced as much as possible. So it's almost balanced, and it's not going to have the problem of that common problem, or not really common, but this problem of chaining or even zigzags like this, right? It won't have this, and it's precisely because it's an AVL tree that we don't really have to worry about being unbalanced. We're sort of guaranteed that this AVL tree is always balanced, and you'll see why when we talk about the implementation. Okay, so it's convenient because if we remember, we previously said that our search operation and a couple others, they all relied on the height of the tree, and the AVL tree being balanced means the height is logarithmic, and so we'll have a logarithmic runtime for those operations. Okay, so that's just to say the height, anything that took theta of the height is now going to take theta of log n for this AVL tree. Okay, so this includes search, insert, and delete for an AVL implementation of the dictionary. Now notice that if we do modify the tree by deleting or inserting nodes, we have to maintain the AVL invariant we talked about, which is that the balance factor for all the nodes has to be -1, 0, or +1. And if it's not, then we haven't maintained the AVL invariant. But in order for this to be an AVL tree, which is guaranteed to be balanced, we need to maintain it. So when we change the tree, we will also make sure that the AVL invariant is maintained. So how do we do that? So how do we do that? Well, okay, so let's actually go through the dictionary operations step by step, and we'll talk about how we do that as we talk about each operation. So for search, this is going to be pretty much the same as what we did for the textbook version of the BST. After all, it is a BST, so we can search just the way we did for any other BST, and we go right if something's more than the parent, we go left if it's less than the parent, and yeah, so that part doesn't change at all. Okay, so what changes? Well, for insert, now we can talk about two cases, right? Case one, we have the case where, let's say, if the node insertion into the BST, if it maintains the AVL invariant, and it must maintain it for every node, then we're done. So remember, if it maintains the AVL invariant, we don't need to do anything, right? Because it has to be still balanced and has to still be an AVL tree, and that's why we don't need to intervene. But in case 2, if we have case 2, which says that if the AVL invariant is broken, or in other words, it doesn't hold, in other words, there is some node with a balance factor not equal to -1, 0, or 1. Then what do? Well, we perform rotations. So, okay, now this probably sounds pretty confusing. What do we mean by rotations? And you wouldn't understand it unless you kind of saw a picture. So in just a sec, I'll just show you one example of a rotation, but I will attach a link to a sort of a tutorial which explains things step by step about how to rotate an AVL node or how to perform a rotation on an AVL tree so that we maintain the AVL invariant. So I'll attach that link in the description below, and you should probably read up on that if you're interested. But yeah, it's kind of tedious to explain, so I'll just show an example with it, but I won't explain each rotation. Okay, but there exist 4 rotations, right? So I'll just briefly list them, but you can take a look at that link, and it goes into good detail about how it works. So please do take a look. So we perform these rotations, and then we fix the AVL invariant. And so once that happens, well, what did the rotations do? Well, rotations change the nodes left, right subtree heights. And this is what reestablishes the AVL invariant. right? Okay, so to reestablish the AVL invariant and to maintain the BST property, right? So at the same time, we don't want to make it so that we break the BST property where we rotate something and then now the parent is maybe less than its left subchild or greater than its right subchild. We don't want that to happen. So we must also maintain the BST property. But that's okay because the way we perform these rotations guarantees that it doesn't break the BST property, and it also reestablishes the AVL invariant. Okay, so just listing what kind of rotations there are. There's the right rotation, there's the left rotation, there is a right-left rotation, and there is a left-right rotation. Okay, so these are the four kinds of rotations we have: left, right, left, and right. So there are different situations where we might use different rotations. So it's a pretty good tutorial, the one I mentioned, and it explains each of these and how and when to perform each. So you can just take a look there. Now, maybe I'll just go over a quick example. Let's say we have some chain. This is the simplest example we can use to sort of explain this. So this is what I'll use. Okay, so we have a chain like this, and let's say this node right here is unbound. It doesn't satisfy the AVL invariant because it is right heavy, or in other words, it has a bounce factor of 2. So it has a bounce factor of 2, and therefore it's right heavy. So in order to maintain the AVL invariant, we rotate this, right? So we do a left rotation, and what happens is now this node X, we'll call this node X. Now node X becomes this middle node, and now it's balanced, or at least this node maintains the AVL invariant. So does this one, so does this one, right? So that's what we mean by a rotation. And there are different contexts and different times where you would use, a right rotation, a left rotation, RL right-left rotation, or left-right rotation. And that's all explained within that tutorial. Okay, so the thing to remember is that we must update the balance factors of the ancestors of the inserted node. So we insert a node, we insert some node X, and then it has some ancestor A and has a chain of ancestors. The thing we need to do is go up the chain of ancestors, which is O of H, and we update the balance factors on those ancestors because this X insertion might have changed it, right? It could be the case where inserting X did not change the balance factors, but it could also happen that X caused a change in balance factors so that we might have broken the AVL invariant. So what do? We rotate, right? So we perform rotations. We rotate if necessary. And after each rotation, we simply update the balance factors on each rotation. And this is constant time. So updating the balance factors is constant time after each rotation. So overall, inserting is O of log n. So inserting O of log n. So inserting is O of log n since we have a height which is proportional to the log of the number of nodes. We have O of log n for insertion. Now how about for deleting? So for delete, we first delete just like we would in a normal BST. So like normal. So we first delete like we would in a normal BST, and so assume we deleted like we would have in a normal BST, then it may or may not be necessary to perform rotations. So if it is necessary to perform rotations, then depending on the resulting balance factors of the ancestors of the deleted node, we may have to do a left or a right or left-right or right-left rotation. So whatever the case is, we do the rotation if necessary, and this can cause up to log n rotations. So in the worst case, so second step, we perform rotations if necessary. So we perform rotations if necessary, and this is actually to the order of log n, because there may be log n rotations we need to perform, and now we see that this is precisely O of log n in the worst case. So this is O of log n in the worst case. Now, okay, so we talked about earlier that AVL trees are an example of an augmented data structure, and they're an example of an augmented version of binary search trees. So what does augmenting a data structure mean? Well, augmenting a data structure refers to when we take a textbook data structure and we add operations. So we add some operations to the data structure, and when we do this, this allows us to solve a particular kind of problem or meet a practical requirement of some kind. So in our case, with AVLs, we have faster search, insert, and also delete. So this is a much faster dictionary implementation. So it's a faster dictionary implementation, and that's why we use these AVL trees rather than just the plain old binary search tree that we were using previously. So the question is, you have a data structure you want to augment. You have a data structure you would like to augment and you want to go about augmenting it. How does that work? So you want to augment a data structure. How do you go about augmenting it? Well, how do you augment? First, after we've chosen a data structure, we determine the additional info we want to store. And then after we know what we want to store, we ask ourselves, is the additional info efficiently maintainable, or rather we should say maintainable for each operation that we perform. And lastly, we also want to ask ourselves whether or we just simply implement the new operations using the added information we need. So implement new operations using added info. Okay, so now these are the steps we need to augment, right? So first of all, we have find a data structure to augment, then we determine the info we need to store, then is the additional info maintainable efficiently for each operation, and then we implement the new operations using the added information. Okay, so that's how we augment a data structure. And now we have an example, which is ordered sets. And these are similar to dictionaries. So these are an abstract data type, similar to dictionary, with search, insert, and delete all being sort of the same. All login. With an AVL implementation, these are all O of login. And we also have, in addition to that, we have rank and we have select. So these two are the new operations we will also define for this ordered set. Okay, so let's move everything up. Okay, so for this ordered set, what is rank? So rank, we rank in some ordered set, some key, and this returns the rank of key k. And similarly for select, if we do select some rank, we return the key with rank r. Okay, so we have rank and select. So let's do this one example. Let's say we have an array. 1, 2, I'll just keep it in order just to keep things simple, and just so we don't have to sort of move our eyes all over the place to check what's the smallest item, what's the largest item. This is a simple sorted array. Now, let's say we called rank S, or sorry, this is a set, not a list. So maybe it's a bad idea putting that those square brackets there. Okay, this is supposed to be a set S. Okay, so this is a set S, and we call rank on this set, and we have this ordered set S, and we are calling rank S with key, let's say 9. So we call rank on key 9, and this is going to return 5 because the rank of key 9 is 5. It is the fifth smallest element. Fifth smallest element. So that's why it returns 5 for the rank. And similarly, if we do select, let's say we select the item which is the 6th rank. So whatever's ranked 6th, that's what we return. What's ranked 6th? 1, 2, 3, 4, 5, 6. This is what's ranked 6th. It's the 6th smallest item. So the 6th smallest item is 88, right? 6th smallest item. And in this case, remember 9 is the 5th smallest item, so that's why 5 was returned, which was the rank of 9. In this case, the 6th smallest item was 88. That's why we returned 88, because it was the 6th smallest item. Okay, so now that we have this, can we somehow implement this using an AVL tree? Well, yeah, sure. Well, can we just use a regular AVL tree? Probably not, because rank and select, we can't really efficiently manage these rank and select operations if it was just the AVL tree we were talking about earlier. Instead, we want to use an AVL tree which stores the sizes of the subtrees rooted at each node, right? Another idea is to use an AVL tree which stores the rank at each node, but the problem this causes is that if we change the tree, then we also have to change ranks a bunch of times, and this is going to be almost like linear time, so that's why we can't really do that. Instead, what we'll do is you will say that so this is our implementation. We use an AVL tree and store sizes of subtrees rooted at each node. So if we do this, what do we see? Well, for rank, the rank of, let's say, some node X with the key K, this will be given by, so this is given by adding the rank of the left subtree, plus 1. And why do we add the 1? Well, we add the 1 for X. and we repeat this until we reach the root. Okay, so this is sort of the idea we have. Now let's say we have some kind of example. Let's build some random example. 32. This is going to be 40 here. This might be 28, right? Here we have 60, and we have 50 here. Okay, so let's take this as an example. So this is our example, and we want to get the rank of x with key k. So let's say we want to get the rank of 32. So we want to get the rank of 32. Well, we follow this algorithm, and we first thing it says is add the rank of the left subtree plus 1. So the rank of the left subtree, this is always going to be 1. Remember, the left subtree has rank 1. All the leaf elements must necessarily have rank 1 because their subtree is size 1. So this is going to be 1 plus, we go up here, 1, because this 1 we added is for itself, and then we go all the way up to the root. So now we're here. So far we have 2, rank is 2, and then what do we add? Well, we go up here, and we go to 44. We see that we can't really add the left subtree of 44 because 32 is in the left subtree. So if 32 was in the right subtree, however, then we continue sort of doing this. But since it is in the left subtree, we don't really do this. So the rank of the left subtree plus 1, so for x itself and its left subtree, is what got us this rank of 2 in this case. And indeed, if you sort of if you take an in-order traversal of this tree, you'll see that 32 is the second element. It's the second smallest element here, and indeed it is rank 2. Okay, so that's for rank. How about for select? So, okay, we can talk about select as well. So for select, we first get the rank of the root, and we call that root's rank. Let's call it P. And if P is equal to the rank we're looking for, so R, remember R is the rank we are searching for, and P is the rank of the root. So we compare the root's rank with the rank we are searching for, and if they are equal, then we're done. Otherwise, if the rank of our root, if P is less than R, so if the rank of our root is less than R, well then in that case, what do we do? So if we need the lower rank, then we go to the left subtree, right? So if we need the higher rank, then we go to the right subtree and search for R minus P instead. So in this case, what do? We need a greater rank. So we need a greater rank, so we go to the right subtree and we search for R minus P. and search for r minus p. And if, let's say, p was greater than r, or in other words, the rank we're searching for is less than the roots, then we go to the left subtree and search for r, right? And here you may be asking, why do we search for r minus p instead of r the way we did here? Well, if you remember the structure of an AVL tree with if we have stored these sizes, the sizes don't really discriminate between if you're in the left subtree or the right subtree. The sizes themselves are just recording what is the size of the subtree rooted at some given node, and that doesn't really differ between the left and the right. So we will not get any difference if we just go to the right subtree and search for r minus p, so, or rather we search for r. So that's why we need to do r minus p and then search for r minus p instead. And that's what's going to get us the thing that is the rank, the thing that's going to be the rank p, or rather the rank r. P, remember once again, p is the rank of the root. So I got myself confused there, but yeah. So to get r, we'll need to do r minus p. Okay, so that's about all with that's about all we need to know with this concept of rank and select and ordered sets. The whole idea with ordered sets was just to put into perspective that there are a lot of considerations we need to make when augmenting a data structure, and we need to make sure that anything we add, any operations and things we add, can be done efficiently, and the data we previously maintained and the new data we want to maintain can in fact be maintained efficiently. And if that's not the case, then we haven't done a very good job of augmenting the data structure. In this case, we have done a good job because we have ensured that everything we do is maintained in logarithmic time, and everything we do is sort of done efficiently. Now, the last thing I want to end off with is a theorem. So there's this theorem so this theorem exists in the algorithm Introduction to Algorithms textbook, the CLRS textbook, and the theorem goes like this. So if some added info does not depend on some node's parents, which means that if it only depends on itself and its children, then necessarily we see that it can be maintained with insert or delete taking place in O of log n. Okay, so what it says is some info, if we have some added info and that does not depend on the node's parents, then it can be maintained with insert and delete in O of log n. So hopefully you try it out yourself. I think augmenting a data structure is one of the more exciting parts of this field of computer science. Looking at data structures and augmenting them is, in my opinion, very exciting. So if you ever go to HackerRank and there's some problem that lends itself to augmenting some kind of data structure, maybe that's a good idea to try it. But thanks for watching.